Okay, so if we look at rates of deposition in terrestrial systems have been well constrained for a long time based on optically stimulated luminescence, OSL dating, carbon-14 and other dating techniques. So we can construct diagrams like you see here on the right by Mael 2015 for terrestrial and shallow marine systems, where we can kind of date the time required to deposit bed forms and look at deposition rates for everything from bed forms to channel belts to basin fills. So the question is, and the question I'd like to pose in this talk, is where do submarine fans fit on this graph? To date, rates of deposition in deep water have been much more poorly constrained than they are in shallow water settings. Part of this is just a great cost due to sampling deep water systems. We saw some great talks about monitoring active processes in fans, but that's very new technology. It's just being published recently by groups like Peters. And interestingly enough, optically stimulated luminescence dating, OSL, has not been widely used in deep water. I'll show you in this talk, we gathered quite a bit of OSL data on the Golo fan and got really excellent results. And OSL dating is very important because it covers a key time kind of period between about 40,000 and it's accurate between carbon-14 dates are good up to about 40,000 years ago. OSL dating can go back as far as 200,000 years ago. And of course, many fans have been inactive over the last 14,000 years or so due to rising sea level. But, as we all know, working deep water, submarine fans are some of the largest sedimentary bodies on the Earth. So being able to constrain rates of deposition on fans and understanding the time required to deposit fan architectural elements is important, because these fans are important recorders of sediment flux and climate through time. Oops, sorry. Okay, so what do we know about rates of deposition at the bed scale? And this is something that groups like Peters have really, given us some huge insights in the last few years about how fast deposition goes on, rates of deposition driven by individual turbidity currents. So you can see on the top this beautiful illustration by Zavala et al. 2017, where they were able to look at this very long-lived flow in the Congo fan that lasted for over a week, compared to other much more short-lived fans and steep gradient systems like Monterey, UMA, or the VAR, where individual flows last for a matter of hours. So we can see that individual flows are capable of achieving velocities of up to 8 meters a second, run-out lengths of over 1,000 kilometers, and can transport over a cubic kilometer of sediment in a single flow. So if we look on the right, this bed from Pliocene deep water rocks in California, a bed like this may represent a few hours of flow. And we saw in some of the talks yesterday from Peter's group that there's a high degree of unsteadiness in flow, so multiple beds could represent a single flow that was deposited over hours or at most days. So what about rates of deposition at the kind of architectural element scale? And we'll show you some more data that we've gathered on the Golo fan from this, but it's a really nice paper by Maslin in 2006 showing the avulsion of elements on the Amazon fan and dating them with carbon-14 dates. And he was able to show that these individual avulsions and extension of these channels occurred on the scale of 4,000 or 5,000 years for each avulsion and extension. So large levied channels, in this case, levees up to 100 meters thick, can avulse and extend over 100 kilometers in 5,000 or 6,000 years. So if we look, for example, to outcrops of like the Karoo Formation, so some of these bodies that might represent, well, in this case, depositional lobes we might expect to be deposited on similar time scales. We'll get on more detail on this in a minute. And then, of course, what's the rate of deposition at the scale of individual submarine fans? And there's kind of limited data on this, but from what is available in the literature, we can see that individual fans with areas of up to 10 to the 6 square kilometers and thicknesses of over 1,000 meters can take anywhere from 100,000 years to tens, to several million years. For example, a Congo fan that we've talked a lot about in this conference, there's there's some ODP data on the edge of the fan that suggests the entire fan was deposited in about 800,000 years. It's got an average thickness of about 2 kilometers, which gives us an average rate of deposition of something like 2.5 meters per 1,000 years. So I'm gonna talk in more detail now about the Golo project, which Gladys and I worked on at ExxonMobil. Gladys alluded to this a bit in her talk. It's a multi-year research project between Ephemer, Total, and ExxonMobil. Started in 2008. We cut 5 cores and on the system, and then shot high-resolution seismic and high-resolution bathymetry. And importantly, we did a pretty extensive dating of the cores using optically stimulated luminescence, carbon-14, and tying to oxygen isotope curves. So we're able to develop a stratigraphy going back about 400,000 years for the development of these submarine fans. You can see the setup. Again, Gladys alluded to this before. There's 2 submarine canyons, North and South Golo, and they feed these depositional lobes or fans kind of at the toe of slope. And so what do we know about that? So we were able to, in the Golo system, we were able to construct a chronostratigraphic framework by mapping individual depositional elements using seismic data, high resolution 2D seismic data. And then we were able to provide dates from the cores, which were tied to the seismic. And we used a number of different dating techniques, as I alluded to, carbon-14, optically stimulated luminescence, and oxygen isotopes to create a stratigraphy going back about 450,000 years. And then here we primarily tied this to the sea level curve, which is shown below. So it looks like the main driver for submarine fan deposition is sea level, and its control on bringing sediment sources into contact, fluvial and deltaic sediment sources into contact with submarine canyons that then allow the bypass of sand into deep water. So we see sandrous deposition correlating to glacials, periods of low sea level, when sea level dropped below about 60 or 80 meters below current levels. Basin-wide muds and carbonate-rich marls were deposited dominantly during periods of higher sea level across the basin, though we do see quite thick muds deposited at the edge of submarine fans when they were active during periods of lower sea level. So, so it's this sort of kind of glacial, interglacial time scale of 100,000 years roughly. We see deposits up to 100 meters thick on each fan, but they can vary by tenfold. So you can see these kind of purples here, like 100 meters, and the margins of the fan may be 10 meters or tens of meters. There's 2 submarine canyons, each feeds a separate fan. We think that avulsion of the Golo River across the shelf activated one or another of these canyons during a period of low sea level, and that each of these fans, and you can see scale here in kilometers, was active for periods of tens of thousands of years. Of course, where you sample on these fans, if you were thinking about rates of deposition, is going to vary enormously because fan thickness varies so much. So if this package represents 10,000 years, and if you had a sample on the fringe, you'd see much lower average rates of deposition than you'd see at these kind of channel lobe transitions where the deposits are very thick and rates of deposition are very high correspondingly. So if we look at deposition at the fan scale, and this, I know it's a lot of data, but these 2 fans, these are marine oxygen isotope stages. You can see the duration in thousands of years. So marine oxygen isotope stage 1 lasts 14,000 years. We see essentially no sand deposition, but we see sort of a tenth of a cubic kilometer of mud deposition across the fan. Then you can see when we go into marine oxygen isotopes 2, 3, and 4, when sea level is relatively low, period of about 70,000 years, we start to see sand deposition.
2 minutes left.
Similar. Okay, yeah, very good. Similar volume of mud deposition, but maybe like twice the volume of overall deposition across the fan. So significant volumes of mud deposited even when sea level was high. At the channel and lobe scale, we see these individual elements, which Gladys talked about in her talk. And we can see, based on OSL dating, you can see get very high rates of deposition at the channel lobe transition, with up dip end of the lobes up to 25 meters of sand being deposited in 3,000 to 7,000 years. And so individual lobe elements, we could see locally very high rates of deposition with somewhat lower mean rates of deposition. You see here like a meter per 1,000 years, kind of on the average, and locally much higher rates where the sample was near the channel lobe transition of up to 10 meters per 1,000 years. And this compares, we see instantaneously high rates at channel lobe transition, say on the Congo fan data, where they were able to, you can see the kind of rates here, 10 to 12 centimeters per year based on using cesium dating of very recent deposits, which are deposited in kind of in the time frame of atomic bomb atmospheric testing in the 60s and 70s. So in conclusion, we can see that, going back to the original question, where do deep water deposits fit on this chart by Mayal? That, and this really should not be a surprise given the work that, we've seen in monitoring submarine fan, turbidity current deposition, that we can get locally very high rates of deposition, very much compatible with what we see on deltas in rivers, and that in some cases even higher on submarine fans when they're active. And so I think this is continuing ongoing work. As we're through time, we'll get a richer set of age dates across submarine fans. But I think this kind of points us in the direction that these systems, when they're active, we can get very rapid rates of deposition and building of the fan. Thank you very much. Oh, and I'd just like to say that, finally, to just acknowledge ExxonMobil, Total, and IFREMER, who funded this study and gave permission to publish the results, and our colleagues at IFREMER, led by Gwenaëlle Joët, who did an outstanding job and worked with us on data collection. And if you're interested in more details, we published a paper in the October issue of Geology on this work. Thank you.